Good morning, everyone. I'll be mostly talking about the formal introduction to matched filtering and the significance of the detection. Let's first outline my talk. First, I will formally define what the detection problem is. Just to carry forward from yesterday, that will be the needle in the haystack problem. Then I will try to motivate that Fourier transform that we have discussed yesterday quite long. It's the simplest matched filter possible with the same animations I showed yesterday. Extending that argument, I'll introduce the general matched filter, which will be nothing but something called noise-weighted inner product that I will define. Then I will talk about different SNRs that we use in our GW literature, and mostly focusing on compact binary coalescence searches. I will show how we do matched filtering using gravitational wave templates. Then I will introduce the template banks and how to do this search low latency, means finding that signal much faster using something called marginalization. Then I will discuss the statistics of the detection problem, significance, and finally, I will just introduce the consistency checks when there are non-Gaussianities present in the noise. So what is the detection problem? In general, if we have a detector, we just want to know we have detected any signal or there is only noise. This seems trivial when the noise amplitudes are subdominant compared to the signal present. But it's not very straightforward when they are comparable, and even in our case, it becomes more severe because the signal has order of magnitude higher amplitude, and it's the noise have order of magnitude higher amplitude than the signal, and the signal is buried deep inside the noise, just like we have seen. So the noise can be of the order of 10 to the power minus 19, 10 to the power minus 20, whereas the gravitational wave signal amplitude can reach as high as 10 to the power minus 22. So there is an order of magnitude 3 difference. So it really becomes a problem for gravitational wave, and we should address it systematically. So let's formally define the problem is, what the problem is, and people are familiar with the Bayes theorem. Should I need to explain it, the conditional probability and all? You can raise hand if you want, I can explain it. It's fine? Okay. So we have two hypotheses. One is the strain data given by the S of t contains only noise, and the alternate hypothesis H1 is that the strain data have noise as well as the signal template or the signal Ht within it. So these are the two hypotheses, H0 and H1. What we want to define, the odds ratio, which is the ratio of the probability of the alternate hypothesis given the strain data and the probability of the null hypothesis given the strain data. We use the Bayes theorem and rewrite the odds ratio as the following. With these two factors, the first factor is the prior odds. That is, without going into the computation, given the data chunk, only from our prior knowledge, what we can say about these two hypotheses. As an example, Ankur told you yesterday that there are only 300 seconds of GW signal that we have observed so far, given the observing run of 10 to the power 8 seconds. So this ratio becomes 300 by 10 to the power 8 naively, just roughly I'm saying, because for us to find a particular signal given a data chunk is highly unlikely. We are not observing the gravitational wave events so frequently such that this number could have been higher. So this is really small. So to get a large odds ratio, the next factor, which is the likelihood ratio, has to be really large. And I'm just going to define formally the likelihood ratio in the coming slides. Okay? So likelihood ratio is nothing but the probability of the data containing, assuming our alternate hypothesis H1 is true, given by the probability of the data that there is only noise. Okay? So at the end, performing this exercise, all we could be able to say is that the data is this odds ratio times more likely to contain a GW signal than to consist of pure noise. Is this philosophy clear so far? Is there any question? Okay, let's move ahead. And one more thing, we need this search algorithm to be really fast, low latency, such that we need to point telescopes if there were any EM counterpart produced by this particular event. We need to tell our EM friends that look at that particular sky patch and all. Okay. You have seen these slides, but I will again go through it with a slight different intention. For a start, that let's assume that there is a monochromatic signal inside the data. And by the data, recall the discussion yesterday, it is of finite interval. Its sampling frequency is more than twice the maximum frequency that we expect to be present in our signal. So we want to find that there are only a monochromatic signal present. So we do a particular Fourier transform. For the Fourier transform, we need windowing to prevent spectral leakage and so on. So when you do Fourier transform, again, we take the monochromatic waves with different frequencies, slide and multiply it with the data and compute the integral. Frequencies, when the frequencies are low, there are alternate cancellations of positive and negative contributions. So we get nothing. Same thing happens when the frequency is higher, and only when the frequency matches with the injected frequency present in the signal, we get a large contribution. So in this particular exercise, what we are really doing is we are matching the data with the simplest filter at our hand, which are the sines and cosines. Extending this argument, formally we can do the same for any general pattern that are present. That are the gravitational wave templates that we have, that Priyanka generated yesterday. Instead of those sines and cosines, we'll use those chirp signals, slide it across the data, and calculate a convolution time series. So we'll discuss this in more detail in tutorial 1, 4.1 today. And if you know some properties of the Fourier transform, convolution becomes a product in frequency space. So given our data chunk, we take a Fourier transform of the data. We have our template. We take a Fourier transform of that and just multiply these two. And since the template will have contributions from many frequencies, we finally need to take an integral over the frequencies. So this is our detection statistics for now. Let's call it a naive matched filter. I will come why I'm calling it naive. It's almost correct, but not quite. Why is it not? Let's go through another example. So instead of monochromatic signal, now let's have a sine Gaussian in the data. Okay, so this template has 5 parameters: the amplitude, the frequency of the sine, the phase in the sine factor, the time when the signal peaks, and the exponential fall off. So about this particular signal and its parameter estimation, when we should vary all the parameters, almost all the parameters, it will be discussed in detail tomorrow by Anjali. But for now, I'm going to fix all the parameters but alpha. So what I do, I generate templates varying alpha. I already have the Fourier transform of our data. I calculate the Fourier transform of this template for each alpha and try to calculate our naive matched filter. What do you think? So I have injected alpha at around 2, and I'm saying I will calculate this quantity for all the different alphas. Any guess what will happen? The thing should peak at alpha equals to 2 or something? It should, right? Okay. It does not actually. It just monotonically increases. Our naive match filter is unable to recover the injected alpha from the signal. Why does it happen? So to understand that, let's really again rethink what is happening when we're multiplying the data and the template. For alpha equal to 5, alpha equal to 0.5, the template is given by the orange dashed curve, and the injected one was there. Let's forget about the noise right now. So everything matches. Everywhere we have positive contribution and we are getting some number. Now we increase alpha from 0.5 to 2.5. The injected template now have more power within it. So when we multiply this data and this template and calculate the integral, just because the injected template at alpha equal to 2.5 had more power, sorry. We are getting more contribution from that naive match filter. So what you are doing essentially when you are calculating that frequency integral, you're multiplying this injected template along with noise. So there was some injected signal with alpha equals to 2. This is the blue one, right? Yes, yes. For alpha equal to 0.5, we are doing this multiplication. And for alpha equal to 2.5, we're doing this. Clearly, just because the exponential fall of time is larger here, this multiplication and integral will give higher value because every other thing matches. Okay. Right? Okay. Just because we don't have normalized templates at our disposal.
I see.
Is this idea clear?
By normalization, you mean you would divide by the frequencies?
We'll see what will happen.
Okay.
So if we can normalize the naive match filter, that might solve our problem. So by normalization, what I exactly mean is that I compute the autocorrelation function of our template in the frequency domain and take a square root. So if you do that, we can see there is a peak at around alpha equals to 2. So when we normalize our particular template to search for that particular template in the signal, that match filter is the correct match filter, which can find the signal in the data. So I have shown the amplitude. Now let's do the same exercise for the frequency of the sine wave. Sorry? Oh, so in case of cross correlation, you had S and H, two different functions. In case of autocorrelation, those two functions are just the same. So you sort of calculate the power. It will be a mod square, right? Mod of H squared HF. It's just the power computed.
With itself.
Yeah. And we have to take a square root because in the numerator we have amplitudes. Sorry, we have to take a square root because finally we are calculating the amplitude. This gives you power. This square root of power is sort of, this is amplitude square, one amplitude in the denominator. Finally, you're getting back the amplitude, right? Now, we fix all the other parameters and calculate the same thing, do the same exercise to recover the F naught. Now we calculate the correct matched filter and you see the sharp spike. So this is F by F naught, so you should see the spike at around 1. And note the discriminating power of matched filtering between amplitude modulation and the phase modulation. So when we are changing that alpha, we are barely having a particular peak. It was the other parameters were the algorithm was not able to distinguish in some sense the other templates very well, but in case of frequency, there is a sharp peak compared to the amplitude. It happens because there is this positive and negative contributions that contributes drastically to that particular integral when you slightly change the frequency of the sine wave. Is this clear, or you can ask if you...
Here you are considering alpha equal to 2 and you are getting a peak.
Everything, here I fix everything at the injected values.
Yes.
And only vary the F naught. At a time, just for this purpose, just to derive the matched filter, I'm changing only one parameter. Okay. So this will be extremely important in case of GW data analysis, that we can actually capture the phase modulation extremely well with this particular algorithm. Because this is F by F naught. So F naught was the injection, right? Yeah. Okay, I'm varying F naught, but let's call it F for now. So that's the frequency. I'm varying the frequency and creating the...
F naught is your injected value. And in that formula, instead of F naught, just write F and vary that F.
And create the templates and compute this particular thing for all the different templates. S was this to begin with, right? S was the full thing. You have n of t and then h of t given by this with F naught equal to 10 Hz. Okay. Yeah, so I have just, in that particular plot, I have just divided the axis with 10 Hz. That's why it peaks at 1. Okay. So when you vary alpha, what actually happens? The phase of your signal does not change, right? The exponential fall off changes. That means the amplitude is modulating by changing that alpha. But when you change F naught, increase F naught, then the phases are also changing, right? So that is the phase modulation, and changing alpha is the amplitude modulation. And just because Fourier transform, matched filtering, calculates the phasing pretty well, because we are just multiplying it at its time frequency in the frequency space, the power of matched filtering to capture the phase modulation is extremely well. Right? Okay. Yeah. Yeah. You always write. Yes. Any other questions? Yeah. So, pardon my access. I could have done it. Just think it like 0, 10, 20, 30, 40, and 50 Hertz. We have F naught is 10 Hertz to begin with. I should have written here F. Sorry for the confusion here. Okay. Louder, please.
So the takeaway home statement you want to say is the peak here is very sharp. Go back to the
Yes,
previous
exactly.
plot.
Sorry.
In the alpha one. Here it's like
It's barely a maxima,
yeah,
I would say.
peak. Yeah.
But there is no
Flat.
peak here. But just because the phasing is captured
Better.
very efficiently using match filter, there is a sharp peak here.
Oh, so you are trying to say that we are essentially designing a filter and we have to know what kind of filter to weave. So based on the sensitivity of the filter, if we want to pick out the phase, we should do this.
Yes. So it's again the needle in the haystack problem, right? You have to know your method to find the needle in the haystack. Here the method is match filtering. Sorry. So here I have done some kind of cheating so far, and none of you pointed it out. I have not talked about anything about what my noise was, right? So the noise was purely white. I have taken an extremely small amplitude for that white noise, such that we can do this toy example nicely. But situation is in gravitational wave data analysis is not that simple. So we have to take into account the colored Gaussian noise, the non-stationary colored Gaussian noise, and we should be able to, even then, we should be able to derive at that same expression, and let's formally derive the noise likelihood. Okay? So what we have at our disposal, we have a finite time observation, and we have a sampling rate of Fs given by 1 by delta t. And if we have white noise, then we can write the PSD as the following. So this is just some form of the mean energy Ritesh has talked about in case of white noise. And I have written, but this is really independent of frequency for now. Let's do it for the white noise only.
Is that delta T or delta F?
It's delta T. So let's X be our random variable, and we have observations only at xj's given by j delta t. The setup is clear, right? So
that sigma square is actually NT square mean.
yes,
NT, not NF.
Yes.
I think you should write the sigma. What is sigma? Variance. Sigma square is, yeah, sigma is standard deviation.
so what this actually means is that at every point, if I have a noise realization, it will follow this particular Gaussian distribution with standard deviation sigma centered at 0. If we have only noise, then the realizations that we are going to get at each xj is then the probability is given by P of xj at each point is just the Gaussian probability. And we are deriving the noise likelihood. Therefore, all n points, so j here runs from 0 to n minus 1. This will be the probability for each of those points, and they are independent because we are assuming that the noise is stationary. So the noise property is not going to change with time. And we can write the total probability as that. So I have just multiplied this n times. So that means P of xj is given by that. Okay, so I can derive now how to get from here to there. Is this particular thing clear? So we have Gaussian probability at each xj, and we have n number of those points. So this is the total probability of that, because they are just independent. I'm just multiplying those. Okay. So I multiply a delta t here, also here, and write this discrete sum as a continuous integral, and just recognize that this is nothing but Sx. So 0 to t square delta t. So this is the power in time domain. This yes. So Sx is the PSD of our noise. So this is, you can derive this to be this, but for now, you assume that at each point, the noise probability is Gaussian with the variance sigma square, or the standard deviation sigma. Okay? And if you assume that, you can show that Sx, the PSD of the noise, the white noise, will come out as this.
It's not clear how on the left you have one frequency at which you are calculating the PSD, and on right, how that frequency is entering. Like you have to,
Sorry, what?
for example, the definition that I had given, n tilde f. So you have to do this mean at that particular frequency and then multiply by a resolution delta f.
Okay.
Here, the right hand side,
I think there is some problem with the convention that you used and I'm using currently.
I think it's just about information. I'm not saying this is wrong, but
What is missing is, so he gave a definition of Sx, some integral, which, and how does that integral reduce
the point
to
is, I
this
remember
Sx?
what was the definition of Sx I am using here.
Okay, we can discuss in the
we can
tutorial.
discuss this later.
Do people understand what is xj, just xj, or just x?
Yeah, it's a good question.
Have people understood that? Xj is the noise at time j. Okay. And the probability of getting that noise xj is given by p of xj. Okay. And then this formula, px and a curly braces xj, that is the probability of getting a stream of noise numbers for j from 0 to n minus 1. So like n numbers. and we are assuming that each of those occurrences are independent of each other. So that's why you are getting that probability for a set of xj.
What you mean to say is we have our time series in our detector. We have saved it at some discrete xj's, so tj's. And now we are asking the question that what is the probability that at just these timestamps, this is all noise, all white noise in this case. Yeah, given that it is a Gaussian noise, we are saying
What is the probability for this total time of observation time chunk to only contain noise? That's what I'm asking right now.
And it's you were saying white noise. It's not it. The shape
this is
of
white noise.
the shape of Sx will determine whether it's going to be white noise or not.
All right.
And at all these time steps, since they are independent, we could just multiply this
Yes.
probabilities
Yes,
and say
yes,
that
yes.
this is it.
So now the power in time domain can be converted using the power in frequency domain. So I'm just going to quickly write everything in frequency domain. It was minus infinity to infinity. I have made it 0 to infinity with, let's also change this factor. And let's put this Sx inside. It was independent of f anyway. This is what we have here. So this noise likelihood is correct for sorry for the technicalities, but okay. This particular noise likelihood was correct only for the white noise. But what happens when you have colored noise? So let's assume we have a filter, capital K of T, that acts on this particular time series and produces a noise that is colored. That is our hypothesis. Okay? So this is just cross correlation. Again, you take Fourier transform of that, and then essentially the new noise model, the Fourier transform of this new noise model gamma of t can be written as the multiplication of the Fourier transform of capital K and x tilde of f. And if you recall the definition of Sx of f from yesterday, I think, yeah. Then we can derive what is S gamma of f using this same definition. So let's just use this particular definition and write and if you substitute this in this, finally substitute this equation A here, then you can show that S gamma of f is given by okay. Then from
X of
the
F is white noise in A.
sorry.
X of F in equation A is white noise.
Yes, but we are multiplying it with a filter to make it colored. I have to do this in this way because there is no straightforward method to produce white colored noise in time domain apart from coming from the frequency point of view. So you have your frequency amplitudes, you make it frequency dependent, go back to the time domain, and you get colored noise.
So we have the answer for the probability that all the data at this in this time chunk is noise if it was white,
Yes.
that simple formula.
Yes.
Now we are trying
Saying
to
that we have multiplied it with a filter.
one second. So now we are just asking if we had colored noise, what is the probability that at this time chunk everything was noise?
Yes.
Right. And there is some way we are doing it.
Yes.
But that's the question we are asking.
Yes, yes, exactly. Yeah. So I just replace that equation with all the things that we have here. And you can show that from here, I replace everything that I have derived earlier. I replace x of f here, s of x here. Let's make it function of f anyway. Then we can go to that particular equation. So the term with the factor 4 in that particular frequency integral, we call it the inner product between two quantities, a comma b, and define it like this. And if you again rename gamma as x and now call x as colored noise, this is the final Gaussian noise probability, or what we call the likelihood for pure noise in this particular data chunk present. So we only know the noise property in our gravitational wave data analysis that we can only derive. We don't know the probability of our signal, but we'll show that just knowing the noise probability will be sufficient to do the match filtering. Sorry?
The x's here are noise.
Yeah.
Okay.
So x, as Ritesh pointed out, earlier I defined x to be white noise, but I have assumed that linear filter, the convoluted filter there, and now I'm calling that x's are colored Gaussian noises, non-stationary colored Gaussian noise. If it was a little bit messy, then I think you can follow the steps by your own and it will be clear. Is there any simple questions on that? Yes. So exponential minus xx. So we define that x comma x to be 4. We don't really need to put the real part because the modulus will be real anyway. This is the quantity that is in the exponential, right? And see, now we have a noise weighted inner product at our disposal to compute the noise likelihood. Yes. You can ask.
So we are measuring the probability of there being noise.
Yes.
So
precisely.
if there wasn't noise, like what should be there?
We'll come to it.
Okay. Okay.
What do you mean by, sorry, what do you mean by there's no noise?
I mean, see, you're measuring a probability that there exists noise.
Yes.
So there are also like one minus of that will be probability that there is no noise. No?
Yes.
So that means there is a chance that
We're
there
going to do something similar. You are on the right
Just
track.
one thing
Yeah.
is missing when he's saying we are asking the question, there is the probability of noise. No, we are asking the question that there is just noise. No data, just noise. So
Oh.
1 minus it would be data, signal plus noise. There is some signal.
Okay.
Not quite. I'll explain
Oh.
what happens later. But the point is, we know the probability of just noise pretty well, and we have derived it robustly. Okay. Good question. If I understood correctly, you were thinking that this is the probability of there being noise. And that's why you said 1 minus that. No noise.
Yeah, that's what I understood. But okay, I guess that's not the case. Probability.
Understand when he says, for example, without the color, the case where you had a single signal for all the. Do people understand how it will generate a noise process? At each time stamp, you sample one number from a Gaussian distribution. Right? You keep doing that. Okay. So, in this way. So what he really just said, so suppose this is your axis, and what I'm doing is there is a Gaussian distribution here. And what I'm going to do at each timestamp, suppose these are my timestamps, right? I will sample one number from this Gaussian distribution. So suppose the first time I do it, I get something close to this. So this. Okay, then I will sample another number from the same Gaussian distribution with the same standard deviation and zero mean. I will get something maybe this, 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 and so on. This is your noise process. Okay, this generates noise. Okay, so here he had written the probability distribution for a single point. Since the probability of each of these points is independent of each other, the joint distribution of this whole series, so joint distribution means the probability distribution of the full set of these will be nothing but the multiplication of these individual probabilities. Okay, and that's what he had in one of the slides. That's where those powers of capital N came from, for example. And now he's just describing the case when there is some correlation between the different points. That is the meaning of colored noise. Okay, now you can't explain each point on its own. It's not independent anymore. So have people seen multidimensional Gaussian distributions here? How many of you have not seen multidimensional Gaussian distribution? Okay. We can take a detour. Yeah. Huh? Go ahead. Okay. So, and correct me if I'm wrong, because I'm also doing this like after 4 years. So let's just take the two variable case. Okay, so there are two variables instead of one, x1 and x2. xi xj cij inverse xi xj ci okay.
mu2 divided by right. This is correct or is this wrong? Is there some power involved here? Anyway, it's just a constant normalization. Huh? Huh? 2 pi raised to the power dimension. So this is square. And this is just determined. Okay. Right. So this is how a multi-dimensional Gaussian distribution looks like. So this is the 2 variable case. This is some constant factor. This is the usual Gaussian stuff. Here you have 2 variables, so you have multiplication. This mu1, mu2 is just the mean, individual means of the of each of these variables. Okay, and this C inverse, the C matrix is known as the correlation matrix. Okay, it turns out that C11 is nothing but the variance of the first variable. It turns out that C22 is nothing but the variance of the second variable. This C12, it turns out that this matrix is symmetric. So this C12 is equal to C21. It makes sense intuitively also, because what this C12 tells you is how much correlated are these 2 variables. So it's these 2 variables. It doesn't matter whether one is correlated with 2 or 2 is correlated with 1. It's the same thing. So that's why they are symmetric. And let me use the variables sigma 1, 2 for both of these. This tells you how much correlated these 2 variables are. Okay. What do I mean by correlation? Suppose this number is positive. Sigma 1, 2 is positive.
It can move.
This?
Yeah. This is also not right now.
Okay. So in the single dimensional case, suppose I were explaining sampling to you, what sampling from a Gaussian distribution looks like. Sampling from a single dimensional Gaussian distribution would be, this is the meaning of sampling, by the way. If you don't know what sampling from a distribution means like, so suppose you have a 0 mean Gaussian distribution. What do you mean by I want to sample from this distribution? You mean that I want to draw numbers on this x-axis. I want to draw some numbers so that they are distributed in proportion to the probability value of this. This makes sense, right? So what I mean is that the clustering of these numbers should be highest where the probability is highest, and so on, right? So if I take, for example, some interval, say from x1 to x2 here, let's say this is x1 plus dx. Just right. Then I mean that the number of samples between x1 and x1 plus delta x, this should be roughly proportional to the probability distribution function times delta x. Okay. This is what is meant by sampling. This number of points should grow in proportion to the value of the probability. Okay, so this was a one-dimensional case. Now what does sampling from a two-dimensional distribution would look like? So I have now a plane of these two values. Let's take the simplest case first. I am putting mu1 and mu2 to 0. So I will consider 0 mean case only. And suppose that sigma 1, 2 is 0. So there is no correlation between these 2 points. Okay. What will happen is, when you will sample from such a distribution, you will find that there is huge clustering of points near 0 because it's a 0 mean Gaussian distribution. And this clustering will become sparser and sparser as you will go around. So if I were to draw contours mean these correspond to the same probability values. Okay. These will be sparser and sparser. So this is how a 0 mean Gaussian distribution with no correlation would look like. Okay. Now, suppose sigma 1, 2 is positive. Sigma 1, 2 being positive means if I choose x1, if I sample x1 and it turns out to be positive, it is very likely that x2 will also be positive. If x1 that I sample is negative, it is very likely that x2 will also be negative. Okay, this is what a positive correlation would mean. So when sigma 1, 2 is greater than 0. What would it look like on this plot? Any guesses? I just explained to you what correlation means. I'm asking you, what will this plot look like when sigma 1, 2 is greater than 0? There is positive correlation between x1 and x2. Exactly. So your contours will now look like ellipses. Again, there will be, most of the samples will be from the center because of the 0 mean thing. But now, if you draw a positive x1, you will also get a positive x2. There is a very high probability of that. And same for the negative side, right? So this is what correlation means. Similarly, when sigma 1, 2 is less than 0, you will get the opposite things. Right? If you draw positive x1, there is a very high chance that you will draw negative x2 and vice versa. So this colored noise case represents a case where these guys are no longer 0. There is some correlation. In white noise means that sigma 1, 2 is 0. There is no correlation. Okay. This representation that he has been talking about in terms of the noise power spectral density, it is just a frequency domain representation of this correlation. That's all. Okay, so that's it.
You can exactly see it here also. It has some other means, but they are positively correlated. So the points are only in first and third quadrant. Okay.
Okay, just one more thing, since I explained all this. This is also one of the reasons why gravitational wave data analysis is done in frequency domain. One of the advantages of doing so. If you were doing this analysis in time domain, then you would need to construct this correlation matrix, a matrix. So suppose you are analyzing a 1 second chunk of data and you have sampled your series at 4096 Hertz. It means that in that 1 second chunk of data, there are 4096 numbers. In that case, this distribution of this whole chunk will be a 4096 dimensional Gaussian distribution, which means that this correlation matrix will have how many numbers? almost a square. There will be half because there is symmetry, but take that out of it. But what he has just shown you, that if you write this probability distribution, there's the same probability distribution, by the way. This same probability distribution just written in terms of frequency domain things. And what this tells you is that instead of looking at these x1, x2, which are in time, if you look at things in frequency domain, this matrix turns into a single function, which is, in computer terms, it will be a vector. Okay, now you just need to store one value corresponding to each sample to represent the same correlation matrix. So instead of 4096 square numbers, you can just do away with 4096 numbers only. Okay, so this gives you huge savings. And if you have any more questions, ask Neha about this. Her recent paper was all about this. She will tell you all the pains she has gone through to do parameter estimation in time domain. One of the major challenges that she faced was related to representing correlation matrices and so on. It takes up huge amounts of memory and so on.
But of course, you can do all this under some assumptions. So like here we have Gaussian noise. It has to be stationary. Then, so because in time domain, as you saw, there are correlation between the noises, and these correlations go away when you go to the frequency domain. But that is only true if you have stationary Gaussian noise. If you have some other thing, if you have some non-stationarity or something, this you cannot do this. But for our current detectors, that is not an issue. Our noise is mostly Gaussian, mostly stationary, so it doesn't really matter.
All right, let's move forward. So we have an inner product between only the strains, but I have shown you that the matched filter that I have derived earlier had the inner product between the data and the template. So how to arrive there? And hopefully you now recall the likelihood ratio. This was the likelihood of H1 and this was the likelihood of H0. And if H1 has, in our H1 hypothesis, if there are many possible parameters denoted as lambdas, which will be our binary black hole parameter set with some prior knowledge about those possible parameters, that what could be the range of the black hole masses, what could be the range, how in distance they are distributed, and in sky how are they sparsely distributed also. Those will all go into the fixed parameter set lambda. So pi of lambda gives you the prior knowledge about the distributions of such parameters. So we have to marginalize over that particular distribution to tell how probable our hypothesis H1 is. In a sense, we have to sum over all the contributions that H1 could produce by this different parameters lambda to tell how much probable the hypothesis H1 is. This is hopefully clear. So if there was no signal in the strain data, then I have just derived that the probability goes as e to the power half of the inner product of the strain, because now the strain is only noise. But if there is a signal present in the strain, we can write the probability of the strain as the following. So the strain now contains noise plus S is n plus h now, and we only know the probability of n. We can rewrite n as S minus h, and therefore just rewriting the noise likelihood will give us the likelihood of the signal present in that time chunk.
Sorry, what is an example of lambda?
So lambdas are all the black hole parameter sets. So there are masses, spins, luminosity, distance, inclination, and everything. So for now, I am fixing a particular lambda and computing this, because you need to have some parameter to produce H. This will take half an hour more.
I think it's good to have some intuition about this probability. So if you look at it, on right hand side, we have exponential where we have S minus H. Why are we calling it the likelihood for signal S? Does anyone have any idea? And why is it Gaussian? So he just said that this is the probability that the signal that you have in your data, it matches with the template, right? Why is that?
So we see that the signal has two parts, noise plus the strain, h of t. And the Akash and Koustav said that this is the probability distribution that colored Gaussian noise follows, right? So if we subtract from the signal
The
the
template.
H produced by some fixed set of parameters, what we should be left with is just the
Our
noise.
hope is that we will be left with only noise.
Right. And now if
We
we
just
have
write the noise probability.
yeah,
That's all.
we have the probability distribution of the
Exactly.
noise, so we evaluate it on this.
Is this idea clear? Just because we know the probability distribution of the noise, and we hope this H will be present in the data, given the hypothesis H1, we subtract it from the data strain and assume it to be only noise and write the noise probability. Yes, yes.
It basically means if the template that you're using and the signal which is there in your detector, if those are consistent, then what you should be left with is just the noise. And you know that noise follows this Gaussian distribution. So in that case, you should have the highest probability possible. But if the S and H, if the H which is there, it does not matches with the gravitational wave which is there in a detector, you will have some extra values, extra power other than the noise. In that case, you will get a lower probability. And this is exactly how you compute the probability that the signal which is there in your detector, it actually matches with the template that you're using.
And as she will talk about in parameter estimation, we will literally iterate through all the lambdas possible and compute the likelihood and try to move towards the maximum probability possible. That is the idea of parameter estimation. But for now, so with some little bit of manipulation, you can write the likelihood ratio for a fixed parameter set to be this. And now we need to construct a statistics that will maximize this particular likelihood ratio. And we have to respect the overall template normalization. So we do some mathematical jugglery here. I will not go into the details, but if you maximize the capital lambda, then what you will be left with is the same form as the match filter we derived earlier, where just to make things clear, if we take the inner product of H with itself, we'll get something called, let's define it that we'll get rho only, which I will call as the optimal SNR here. So in the numerator, as I have mentioned, it takes care of the phasing, and in the denominator, the square root of the power takes care of the overall amplitude. And it's really easy to show that if universe was kind to us and produced ensemble of same events, like events that have the same lambda, then the distribution of rho MF that you will get, and we can compute the mean of it, then we'll get this particular rho to be the mean. So the matched filter SNR, we call this rho MF to be the matched filtered SNR, and the mean, if we could have calculated, we call that optimal SNR. So you have that likelihood statistic derived, you maximize it, and you arrive at the matched filter SNR. Okay? What is this? So if the optimal SNR is the mean, using this formalism, you can also derive what is the standard deviation for that case. And I will not go into the details of that here. You can calculate it. Just like I have calculated, you have the expression for rho mf lambda. I've computed its mean. You can also compute its standard deviation. Okay, so our next job, so we have derived our likelihood ratio or Bayes factor for a fixed lambda. We now need to marginalize over these different lambdas and arrive at the total Bayes factor in the problem, in the search problem that we are after. So before doing that, a quick recap. I think I will skip this, but the point is there are 5 parameters: right extension, declination, luminosity distance, the inclination angle, and the polarization angle, which you can combine to form an effective amplitude. And in this particular matched filtering case, since you are normalizing your power anyway, you get the amplitude for free. So you don't need to worry about all these 5 parameters. What you are left with is M1, M2, and the spins, and the arrival time and the phase at arrival. So, and also if you need more physics like eccentricity or tidal deformability for neutron stars, we'll have more parameters, but let's not worry about that for now. So we have those particular lambdas, we calculate the marginalization. Now, if a strong signal is present, just like we do stationary phase approximation, we can approximate this particular integral to be at a particular lambda where this thing maximizes. And this maximization can be done analytically. All right, the amplitude marginalization is free. I think I should skip over this. Now, if we want to know the arrival time of that event, so we'll discuss this in really detail in the tutorial 4.2. But let's assume that our template is given by this, where this mu is all the other parameters except the arrival time, and this template peaks at T0, and you can compute the matched filtered SNR as a time series, and whenever the time series peaks, you can find out the arrival time accordingly. If you have an unknown phase, you can calculate your matched filter SNR at phase equal to 0 and phase equal to pi by 2, square them, add them and take a square root. It will be automatically maximized in phi of c, since we are trying to calculate the optimal detection statistics. So it's again an exercise. You should show that given this form of the signal, you can get this analytically. So the parameters Tc and phi c can be taken care of analytically. What cannot be taken care of analytically are the intrinsic parameters. Therefore, we need to resort to a collection of pre-computed templates to search from. Since we have all those different lambdas, we'll create our template bank for all those lambdas, create those templates and slide through the chunk of the data we are given. This is literally LIGO does, and they have created millions of templates and they use this particular template bank to do the low latency search in real data. So we grid up the continuous parameter space. So the intrinsic parameters were 8 in numbers, but we often see that mass 1, mass 2, and certain combination of spins are sufficient. So it's usually 3 or 4 dimensional. And we sufficiently finely grid this signal parameter space manifold such that the maximum likelihood ratio that can be approximately identified as the best match among the collection. We should not, the true signal at least should lie too close to any of the templates that we have in the template bank. Okay? I think we should skip over this slide in the interest of time. So the idea is whenever in that particular manifold in the parameter space, if you change, if you grow from one parameter to another, if your waveform varies drastically, you should finally sample that particular region. In the other regions where your waveform does not change that much, coarse graining will also be fine. Okay, so you need much more finer resolution when the waveform varies drastically. And we do it by saying that we want our mismatch to a particular level, and that leads to fixing the grading length different at different regimes. So this was the actual template bank used in GWO1 run, and you can see the particular parameters that matched best with the data chunk. This is the first event, GW150914. So matched filtering is central to gravitational wave detections. If we know what we are searching for, if we know the needles what we are searching from in the haystack, but it is only optimal under Gaussian noise. That is the key point. Neha, again, I think she will be mentioning it tomorrow as well, right? So noise modeling and template bank construction are crucial because we can only get statistical properties of noises efficiently in GW data analysis. Modeling the noise as accurately as possible will be really beneficial, and likelihood ratio forms the foundation of detection significance, the capital lambda that I have mentioned. So finally, let's assume we were given a data S of t, and lambda max was the parameter set that produced the maximum likelihood ratio. Therefore, you can say that the data is this times the prior odd more likely to contain a GW signal than consist of pure noise. Okay, I think this slide I will discuss in little bit details in tutorial 1. For now, we can wrap up and move to Ritesh's tutorial, the leftover from yesterday. Okay.
Again, if you have any question, if you don't want to ask it right now, you can talk to Koustav or me or Akash, anyone. Or you can write it down and we can discuss it tomorrow too in the discussion session.
What is the lunch?